Since we began our journey, we've learned some amazing things about woodpeckers. When they peck, they hit the tree going at about 15 miles an hour, and they endure decelerations of up to 1500 G, all to eat, to court, to make nests, and to store food for their families. But the answer to how they withstand these decelerations when they peck is really quite simple. It's a matter of scaling. The size of their brain matters, and their small brains allows them to withstand large deceleration. Scaling phenomena like this are widespread in nature, and many things can be explained by scaling laws. Another example of a scaling law in nature is in the shape of bones. And here we have a variety of bones in front of us. This bone here is the femur of a hummingbird, a very small bird. And these two bones here are femurs from moas, which were very large birds. Hummingbirds are very small. They weigh between about 3 and 8 grams. A penny weighs about 2.5 grams. So a single penny is the weight of a single small hummingbird. And if I had 3 pennies, that's about the weight of a large hummingbird. So they're very small and they're very delicate. The moa, on the other hand, was a very large bird. The largest of them were about 10 feet tall and weighed about 500 pounds. Moas are now extinct. They were similar to ratites like ostriches or emus. They were flightless birds. And you can see one of the striking differences between the hummingbird femur and the moa femur is that the length of the femur relative to the diameter is much larger in the hummingbird femur than in the moa. And this is also the result of a scaling law. When you think of the amount of force that the femur or any bone can withstand, what we're interested in is the force per unit area, a little like we were interested in the woodpecker with the impact on the woodpecker brain. The force is the weight of the bird, which varies as the length cubed. The area is the cross-sectional area of the bone, which carries the weight. The area varies with the diameter of the bone squared. So the force over the area varies as the length of the bird cubed over the diameter of the bone squared. And this can't exceed the strength of the bone, which is roughly constant for different species. Rearranging, the length has to vary as the diameter raised to the 2/3 power. This scaling law applies to other types of bones too. Here we have the dimensions of the humeri from antelopes ranging from the 3 kilogram Kirk's dik-dik to a 750 kilogram Cape buffalo. The length varies with the diameter raised to the 2/3 power again. Scaling laws govern many phenomena in nature. For instance, there's a scaling relationship between the speed of flight and the weight of a flying object. And this scaling law governs everything from the tiniest little gnat to large birds like swans, and even up to the largest planes like Boeing 747s. Scaling laws are universal, and they describe many, many processes in life.